Hello everyone. Thanks for joining us at this presentation on daylight performance evaluation in a modern Brazilian heritage building. This paper reports results from research investigations and simulations conducted in a Brazilian modern architecture icon, University of São Paulo's Faculty of Architecture and Urbanism, also known as FAU-USP. Due to its heritage listed status, much needed retrofit and changes to the indoor configuration of workspaces have been limited, and any modification must consider the architect's original design and conservation codes. This study has two distinct and complementary parts. First is the deployment of post-occupancy evaluation surveys to better understand occupant satisfaction using the Australian tool named Bossa Time-Lapse. And second is the computational performance simulation using Dialux Evo. For Bossa Time-Lapse, results only from questions regarding the connection with the outdoor environment, access to daylight, and visual comfort are reported. Bossa collected 33 responses from all workspaces analyzed. Simulations were performed for summer and winter solstices. Clear and cloudy sky conditions were also considered. The range of 250 to 300 lux was used as the minimal performance criteria for lighting levels. FAU-USP was designed by the architects Vila Nova Artigas and Carlos Cascaldi in the 60s. The Brazilian modern architecture had a remarkable development in the 20th century. The building structure is characterized by a large concrete block supported by shaped columns. From inside the block, the spatial continuity is determined by a large central atrium and ramps that connect all 8 floors. This section shows all 8 floors connected by the central atrium and by the ramps. As part of his practice and main concept, Artigas also implemented passive environmental strategies to his project. The use of a floor-to-ceiling glass windows allowed the access to natural light and outside views, while an extended concrete slab works as a horizontal shading along 2 main facades, protecting indoor spaces from direct solar radiation. The 3 yellow boxes highlight the workspaces analyzed for this study, named here as Workspace A, B, and C. The plans allows us to identify each workspace analyzed in different orientations and floors of the building. The 3 workspaces have similar configurations and are configured as open plan offices, partitions made of pressed wood fiber or dry walls, yellow epoxy for the floors, an exposed concrete slab, 3 meters height from floor to ceiling, and an exposed and extended concrete slab working as shading device. Both the exposed concrete slab and yellow epoxy flooring designed by Artigas are protected from any modification. Results from Bossa survey shows that Workspace A outperformed B and C on questions regarding satisfaction with the amount of light, control over shading devices, and connection to outdoor environment. Workspace B presented the lowest performance of all questions, with the exception of views. Workspace C outperformed the others on questions regarding daylight and view. Workspace A is located on the half underground floor, having a partition dividing the space into 2 rooms. 4 variation scenarios were simulated for Workspace A, named as Simulation A, B, C, and D. Detail about all simulations can be found in our paper. As seen on Simulation D, the overall distribution of light improved when high partitions were removed and the wall and ceiling were painted in white, increasing the illuminance level by 65%. These modifications increased illuminance levels by more than 3 times when compared to the Simulation A, allowing further spaces from window to achieve a minimum of 250 to 300 lux. For any modification proposed, it is possible to achieve an increase of 10 to 50% of the daylight illuminance level. Those results could address reported dissatisfaction regarding the room being too dim. For Workspace B, 2 simulations were carried out. The original configuration, named as Simulation A, and a second simulation, named Simulation B, where the concrete ceiling were painted in white color. None of the simulation achieved the minimum performance criteria of 250 to 300 lux. However, Simulation B showed an illuminance increase of 19%, reaching up to 150 lux in spaces furthest from the window. In contrast, occupants reported dissatisfaction with too much glare from light, too bright environment, and reflection on screen. Both dissatisfaction results from surveys and performance simulation results might be related to the design aspects of the space, so a more detailed study should be carried out. Workspace C is the only office that achieved the minimum criterion for light distribution in its original design, probably because of its shallow configuration. In addition, when modifying the ceiling color, Workspace C exceeded the maximum performance criteria by up to 65 lux. In regards to the occupant survey, dissatisfaction was also linked to glare from lights, which can be related to the layout distribution and design aspects of the space. Combined, modifications proposed here helped increase the illuminance level by 10 to 65% within all workspaces. These results bring out the discussion of how architects should propose modifications on heritage buildings in order to improve occupant satisfaction. The concrete ceiling of FAU USP's building is protected from any modification because of the heritage-related restrictions reflecting the design of an era. However, the study showed that for specific orientations, floors, color of the materials, and space configurations, any modification within the workspace, such as painting the ceiling in white, is required to achieve minimum performance and increase the level of satisfaction of occupants. Further studies should be conducted to address the limitations of the current study in terms of sample size and demographics. We thank you for watching us, and for more information on this study, please have a look at our paper.